Welcome back, class. Today I want to continue our discussion about solutions and talk about solubility, the solubility specifically of ionic compounds in water. Now, most ionic compounds, as we know, or maybe familiar with, are pretty soluble in water, but not all of them are. So we need a way to predict or determine whether an ionic compound will be soluble in water. In order to do that, a set of what we call solubility rules have been generated. Now, these solubility rules can be found in all sorts of different formats. In your textbook, you'll find a more rule-based format. In the slide here, I have more of a grid format. I choose this one because this is the one that I tend to put on exams and so forth. With that being said, these are not rules that you need to memorize. These are rules that you may want to be familiar with, and the more you use them, the better you'll become acquainted with them. But when it comes right down to it, you're going to be able to refer to a table like this to predict the solubility of an ionic compound, as you would if you were working in a lab. You wouldn't want to necessarily rely on memory for especially compounds you weren't maybe familiar with. But I will point out a couple things in here, and that is, first of all, how is this organized? Well, if you look along the top, you have what here would be your anions or your negative ions, right? So these are your more common negative ions, things like some polyatomic ions like acetate and carbonate, hydroxide. And along the side, you see your positive ions. These are your more common metals, right, that are going to serve as your positive ions, along with, of course, the one positive polyatomic ion, ammonium. Now, looking at this, you can pick out a few patterns that I'll just point out. For example, certain metals, certain positive ions, will almost always be soluble. For example, sodium, right? If you go across with all of these negative ions, it's soluble. So, sodium, potassium, again, always soluble. Ammonium, again, look at all these soluble ones. So, at some point, you'll start to see, oh, it has sodium in it. It's going to be soluble. There's also certain negative ions that are either always or almost always soluble. So things like, for example, nitrate. If you look down here, right? It's always soluble. Or if you look at something like a chloride ion here, right? Lots of solubilities. Now, there are a few exceptions, and this is why we have rules, right? We don't need to necessarily memorize every single exception, but we will start to see patterns develop. Okay, so the big thing is we need to understand how to use these solubility rules. That's what it comes down to. So we can look at a couple quick examples that we can use our table to trace. So we got nickel sulfide. So we're going to look for, I like to look for the negative ion, because that's going to be maybe that's how I do it. You could find the nickel as well, but I'm going to find sulfide here, right here, and I'm going to go down until we find nickel here, and so we're going to go across, and we see nickel sulfide right here. It has an S. S means it forms a solid, right? So this would be, is it soluble? No, right? AQ indicates it's soluble, aqueous. Okay, how about magnesium phosphate? So again, I'm going to find my negative ion, my phosphate, and I'm going to go down. I'm going to look for where magnesium is, and I find magnesium right here. And again, the combination of magnesium and phosphate, solid. Now, I might point out as I'm looking at phosphate here, phosphate doesn't tend to form many soluble compounds, right? Again, you start to see patterns. How about this one? Lithium carbonate. So if we look at, let's find the metal this time. So we find lithium, and we go across, and we find carbonate. Oh, it's alphabetical right here. Lithium carbonate is going to be soluble. So it is soluble. And how about ammonium chloride? Well, we find ammonium here. We'll go across to the chloride. And again, we see that ammonium and chloride combined gives you an aqueous or soluble material. So we want to understand how to use these solubility rules. Okay, so when do these become useful? Well, let's look at a reaction. So let's say that I am reacting two solutions. One, a solution of potassium carbonate, and a solution of nickel 2 chloride. So these are the two things I'm going to combine. And I want to know, what are the products of this reaction? Well, before we do anything, let's figure out what these materials are. So, remember, potassium, right? When it forms an ionic compound, it's going to be K plus, right? It forms a positive 1. Carbonate, CO3 minus 2, right? One of our polyatomic ions. So when we write the formula for this, right, it's going to have 2 of the potassiums to match up with 1 of the carbonate. Right? So we're going to have K2CO3. Nickel 2 carbonate, or chloride. Well, we know the nickel here is going to be nickel 2 plus because that's what the nickel 2 means. We know the chloride, right? Cl is always minus. And so this is going to have nickel Cl2, right? We need 2 of these to match up with these. Now, we said we're reacting a solution of these. So this is going to be aqueous, right? And aqueous. So we want to try to predict the products of this reaction. Now, one thing that we want to keep in mind is when two ionic compounds react in solution, they react via what's called a double displacement pattern. Or one other way to describe this is that they ion swap. So in other words, the positive ion in the first compound swaps to pair with the negative ion in the second compound, and vice versa. The positive ion in the second compound swaps to pair with the negative ion in the first compound to give you your products. So if I want to predict what my products are going to be in this reaction, or could be, I'm going to combine potassium, right, with the other negative ion, the chloride, and we got 1 and 1, so my formula is going to be KCl. I'm going to combine the nickel and the carbonate. They're both 2 minus 2 plus, so a 1-to-1 combination. So I get nickel CO3 as my second product. So now I know what the products are. Now, one of the things that we don't know though, and this is where my solubility rules come into play, is I don't know whether these products are soluble in water. So in other words, I don't know if they're going to be aqueous, if they're going to dissolve. That's where my solubility rules come into play. But before I jump to my solubility rules, let's balance this equation first, because now that we know everything that's there, we can balance it. So if we look on the reactant side, we have 2 potassiums. We only have 1 potassium here. So if we put a 2 here, we can balance that. Let's check everything else. So we have 1 carbonate, and we have 1 carbonate. So remember, polyatomic ions that don't change, we can balance as a group. We have 1 nickel, 1 nickel. We have 2 chlorides, and now we have 2 chlorides here. So now my equation is balanced. Okay, so now let's jump back to my solubility rules and check these. So how about KCl here? So let's find potassium, and then let's go across to my chloride. And so potassium chloride is going to be aqueous. And the other one, remember, was nickel carbonate. So let's look at the carbonate here, and we'll go down. We'll find nickel here. So nickel carbonate, this is the box. So that is not soluble. So now we know that the KCl will be soluble, but the nickel carbonate forms an insoluble ionic compound. So what we see here is our reaction going on, right? We have the nickel ions from the nickel chloride combining with the carbonate ions from the potassium carbonate to give you solid nickel carbonate. This is what we call a precipitate. And so, if we want to look at what's going on here, we have what's called a precipitation reaction. And this is simply a reaction in which a solid is formed when 2 aqueous solutions of ionic compounds are mixed. So this is an example of what's known as a precipitation rate, a reaction where we mix 2 solutions of ionic compounds and we get a solid formation. And again, that solid is called a precipitate, and it's a precipitation reaction. And it follows a general format of a double displacement reaction. And we'll see this pattern all throughout this chapter when we talk about aqueous reactions. So let's review here the process. What did we do to get here? So we can break this down into, say, 5 steps. So the first thing we did here, right, was we determine the ions present. So we determined that we had potassium ions and carbonate ions in solution from the potassium carbonate, and we had nickel and chloride ions in solution from the nickel chlorides. We determined the ions present, we swap ions. So in other words, we do our double displacement. We predict the products based on the ion charges. So we swap the ions, we then predict the formula of those products based on the charges of the ions that we're combining. We balance the equation. And then finally, we check the solubility of the products with the solubility rules, right? And the point here is to determine if any precipitate forms. And so we can follow these 5 steps and predict the products of our reaction. And of course, the precipitation is one potential reaction that occur in aqueous solution. And we'll look at a couple more as we go through this, a couple more possibilities that maybe a precipitate doesn't form, but maybe something else happens. Now, there's a couple things that we can look at to maybe make analysis of this equation a little bit easier or make it a little easier to display. So, the normal way that we display equations, right, that we've illustrated here, is called a molecular equation, right? And it's the most common way that we do it. So a molecular equation, right, is simply an equation that shows the complete neutral formulas of each compound in an aqueous reaction as if they existed as molecules. So this is a nice way to show it, easy to communicate, right? But it doesn't necessarily tell us, what actually exists, right? So what we have to understand is when we show any ionic compound as aqueous, what's really happening is these exist as dissociated ions, right? Because when these ionic compounds dissolve in water, they dissociate into their particular ions, their separate positive and negative ions. So a more sort of complete way that we can write that is to write something called the complete ionic equation. And this is where the soluble ionic compounds, or the aqueous compounds, are shown as separate ions, while the solid precipitates, or sometimes gases or liquids, are simply shown as their compounds, right? Because that's how they're existing. So if we do that with this particular reaction, right, the potassium hydroxide gets separated into 2 potassium ions, 2 hydroxide ions, because of the coefficient here. The 1 magnesium nitrate gets separated into a magnesium 2+ ion and 2 nitrate -1 ions. The potassium nitrate gets separated into 2 potassium ions and 2 nitrate ions because of the coefficient. And the magnesium hydroxide solid stays as the magnesium hydroxide solid. And so this gives me a more accurate prediction of what's actually in that flask, right? If I were to do this reaction, I have these ions floating around in solution, right? Potassium hydroxide, magnesium, nitrate ions floating around, to start out with, and at the end, right, I have potassium and nitrate ions still floating around in solution, but the magnesium and hydroxide ions have combined to give me this solid. Well, now while this is useful, it's a bit, so remember, dissociate it in aqueous solutions. But it's a bit cumbersome, perhaps, and so we can write this in sort of a shortened form that only shows the ions that are actually changing, that are actually reacting to form the precipitate, and this is called a net ionic equation. So we do this by taking our complete ionic equation here and removing what are called the spectator ions. So we look for things that haven't really changed, right, that are still aqueous on both sides. So that's the potassium ions here, and the nitrate ions here, right? So those don't change, and what I'm left with is my 2 hydroxide ions combined with 1 magnesium ion to give me solid magnesium hydroxide. And this is my net ionic equation. And it shows the actual reaction occurring in solution. You have removed the so-called spectator ions that remain aqueous in the beginning and the end. Okay, so we can use these different forms, the molecular equation, the complete ionic equation, the net ionic equation, to get a better understanding of what's actually happening. So let's do another example. So let's take this example of K2SO4, so potassium sulfate, reacting with silver nitrate. And ultimately I want to write the ionic or complete ionic equation and the net ionic equation for each of the following. But of course, before I can get to there, I have to write the molecular equation, right? I have to know what my products are. So let's go through my 5 steps that we did to break this down. So the first thing was determine the ions present. So in my first solution here, I'm going to have potassium ions and sulfate ions. So if I were to write that out, I'm going to have 2 K plus ions, right, aqueous, and I'm going to have 1 SO4 ion. Of course, these are aqueous. And then from my silver nitrate, I'm going to have a silver, and it's going to be +1 because the nitrate is -1. And 1 nitrate ion. Now, what do we do now? We swap the ions, right? So the positive ion from my first is going to combine with the negative ion from the second. So it's going to go down here, and the positive ion from the second is going to combine with the negative ion for the first compound, and we get our second combination. So the potassium and the nitrate combine, +1, -1, KNO3. And the silver and the sulfate combine. So we got +1, -2, so I need 2 silvers to go with my 1-sulfate. Now, next step, I have to balance the equation, right? So I'm gonna go rewrite these up here just so that we get it in the molecular equation. KNO3 Ag2SO4. So if I look at my equation, I have 2 potassiums here, 1 here, so I'm going to need a 2. I have 1 sulfate, 1 sulfate, 1 silver, 2 silvers. Oh, so I'm going to need a 2 here to balance the silvers. Get 2 nitrates, 2 nitrates. So now I'm balanced. So I have my products here. Now I'm going to check my solubility. So let's flip back to our solubility table. And again, we had KNO3. So I'm going to look for my nitrate up here. And I'm going to look for potassium right here. And I'm going to see that it's aqueous. And I had silver. So have silver sulfate. So let's find sulfate here. And then let's find silver right here. And so silver sulfate forms a precipitate. Okay, so now we can go back here. And we know this is going to be aqueous. And this is going to be a solid. So now we have our completed molecular equation here. Now we can finish our complete ionic equation. So I'm going to erase the potassium nitrate here and rewrite it as the ion form, right? So 2K plus aqueous plus 2NO3 minus aqueous. Give myself a little more room here. So plus 2NO3 minus aqueous plus silver sulfate solid. So here we have our complete ionic equation. And then, of course, the spectator ions, we're going to get rid of these. And so potassium is a spectator, nitrate is a spectator, and what I'm left with is SO4 2 minus combines with Ag 2 Ag plus. So right, we needed a 2 here and a 2 here, right, and there. Aqueous to give silver sulfate solid. Let's try one more example here. We have sodium carbonate plus magnesium bromide. So I'm going to go through this one a little bit quicker because we just went through the last one in a little more detail. So I'm going to not write aqueous all the time here, but understand that anytime I'm talking about something in solution, it's aqueous, just to make things go a little faster. So again, first step, we're going to break things down, identify the ions present. So I got 2 sodium ions plus carbonate ion. And from here I have magnesium ion plus 2 bromide ions. Now we can swap the ions. So again, the sodium is going to pair with the negative ion, the bromide. That's a 1-to-1. It's in, I'm going to write it up top. So one possible product is sodium bromide, right? NaBr. The second product, the magnesium, will pair with the carbonate. So we got 2 plus 2 minus, so again a 1-to-1 combination. So we got magnesium carbonate. Now, next step would be to balance the equations, right? So I saw what was there, I swapped my ions, I put together the ions to make the products. Now I'm going to balance. So look at my sodiums, I got 2 here. Oh, I only got 1, I need 2. Carbonate, 1, 1. Magnesium, 1 and 1. And bromine, got 2 on the reactant side, got 2 on the product side now with my coefficient of 2. So now I'm balanced. Next step would be to use my solubility rules. Now, I'm not actually going to run through it for this one. I'm trusting now that you can do it. So if I were to sodium bromide, it turns out it's aqueous. Magnesium carbonate is not soluble, so it's going to form a solid. So now we have our molecular equation. Now we can break that down into our complete ionic equation. So we already have the first half. So let's finish the product side. So the sodium bromide will give me 2 sodium plus ions plus 2 Br minus ions that of course are aqueous, but I'm just not going to show it. And my magnesium carbonate precipitate stays as a solid. So here's my complete ionic. So we'll finish out by reducing this down to the net ionic equation, remove our spectator ions, which are sodium, the 2 sodiums here and here, 2 bromides here and here, and we're left with carbonate ion plus magnesium ion gives me magnesium carbonate solid. That's my net ionic equation. Okay, so now we have some good practice using our solubility rules, analyzing and predicting the products for these so-called precipitation reactions, and displaying these as both molecular equations and complete and net ionic equations. Now in the next section, we're going to look at a couple of other types of these aqueous reactions, acid-base reactions, and some reactions that produce a gas.